In chapter 12, we're going to talk about functions. So let's start by introducing what a function is here in section 12.1. So we'll start with our classic example of what we're used to for a function. So maybe we can look at f of x equals x squared. We know that the graph of that function is going to be this nice parabola here that we draw in R2. And what we're going to do is we're really going to think about defining what the graph of this function is, and then doing sort of a new perspective on that, right? So what is the graph of this function? So the graph of f of x is just a set of points, right? I've got all these infinitely many points. So this is just going to equal the set of points where the first one comes from R and the second one comes from R. So it's a set of the points x, y that come from a Cartesian product of R cross R, where the y is just equal to the x component squared. Right, so the y is just equal to that f of x. So in a way, we can think about this function as a set of points coming from this Cartesian product between two sets. So in that way, this function is really just a special type of a relation. Right? It's a relation is just any subset of a Cartesian product. Here we're going to not necessarily restrict ourselves between relations from two the same sets. We could have relations between two different sets. Right, I'm definitely not going to get all of this second r, but the y is still going to be a real number, so it is going to still come from a subset of a Cartesian product. This is what we want to do. We want to sort of change our perspective in a little bit to think about these functions as subsets of relations, and when I think, what extra rule do I need to put onto that relation in order to make it a function? So maybe you remember from pre-calc or something that the big thing that you need to do to check that something is a function is this vertical line test. So let's think about what we're actually checking when we're checking a vertical line test. We're checking that for each element in the domain, there's only one element in the codomain. So we'll see those words in a minute. But right, the domain is just that starting set. The codomain is my ending set. So I'm making sure that for each input, there's exactly one output that gets assigned to it. Right? So the specialness that we need for a function is that each input gets assigned to one output. They can get assigned to the same output. It doesn't have to be necessarily different outputs, but I can't have this point here getting defined also to some other thing. That's not allowed. So it has to pass that vertical line test, but not necessarily that horizontal line test. So let's see if we can change this into a rule about our relation. Okay, so I'm going to have some relation, x, y, and I'm going to say that each element of that first set, that's my domain set, can only appear once as the starting element, and it must appear once, right? I also can't leave off bits of my domain. Every single element in that domain must be mapped to exactly one element in the codomain. So let's see that on the new slide, and we'll define those terms of domain and codomain. Okay, so I've copied our formal definition here from the book. So it says that if a and b are sets, then a function f from a to b, denoted f from a to b. So here, when we're talking about functions, we're going to start being really explicit about saying what these sets a and b are. And it's going to be a relation, so it's a subset of the Cartesian product of a and b. So we're just listing out for everything in a what it gets mapped to. And it satisfies this extra special property that for each element of the domain, so for each a and a, the relation f contains exactly one ordered pair of the form AB. And then instead of writing that AB is in this set F, we're just going to write that f of A equals B. All right, so that is our formal definition in terms of defining the function f as a set In particular, it's a subset of a Cartesian product, so really it's a relation, and it's a relation with that special property that for each element in that first set, A, which we're going to know is going to be called the domain, so let's fill that in at the bottom here. Oops. That A set is called the domain. It's going to get mapped to that one set B, and that B set is going to be called my codomain. Come on, codomain. I'll just go ahead and highlight those two. So we've got the domain, and we've got our codomain. Okay, so what's the less formal definition we'll see sometimes? We could think of it not in terms of sets. So the definition that we often see is that a function, instead of saying it's a set, we'll say is a map or a rule that assigns to each element in some set A, called the domain, as we saw below, exactly one, so it can't be 0, can't be 2, element of the other set, B, which is called the codomain. So this is, again, another definition of function that we might see. But if we ever sort of get stuck and we need to be really formal about things, we can always go back to this set definition. So let's look at some examples and think about how we can change them into those sets. Right, so we saw this f of x equals x squared notation or definition already. So we can think about that in sort of set world as just a set of ordered pairs where I have to have all of the elements from my codomain, and then I map them, of my domain, and I mapped them to my codomain. So when I'm writing this function out, we're going to do this thing where we add now what the domain and the codomain are. So I'm going to say the domain is R, and the codomain is also R. So I'm going from R to R. And then I could start listing them out, right? But I have to have one ordered pair for every single element in R, so that's going to be an infinite set. So instead, I can think of this as the set of x comma y in R cross R, where x squared is equal to y, or y is equal to x squared. Let's write it as y is equal to x squared. Okay. Now for my second one here, my second f, we have a function that's taking in two things. So this f is actually going from R2 and it's outputting 1. So this function is a multivariable function. It's going from R2 to R. So then if I want to write that guy in set world, I'm going to take in two things, x and y. So maybe I take in 1 and 1. And I output the squared added together is 2. So this is going to be my ordered pair. So it's an ordered pair where the first element is also an ordered pair of that x and y. I can take in something like 0 and 2 and output 4 and so forth. Again, there's way too many to list them out. So I can think of this as the set of x comma y as my input, and then z. That's going to be a subset of R2 cross R, where the z is just equal to x squared plus y squared. So that's how I can represent that function as a set. Now for the last one here, this is actually a non-example, right? Here, if I said something like f of 2, I would get plus or minus the square root of 2 squared is 4 plus 1 is 5. So I actually got two answers here. So that means that this is not a function, because there were two different outputs, both the plus and the minus. So we'll see this sort of ties into our discussion later. We have to make sure there's only one output, right? So if I got a quantity like this by trying to solve some expression and I had to have that plus or minus, I would know that that's not going to result in a function. Okay, so as we're thinking about this definition of function, here's something for you to think about. Is the function f from q, the set of rational numbers, to z, defined by f of p over q, right? So anything that's a rational number can be written as p over q, where q is not equal to 0. I'm going to define that to equal p plus q. Is that a function? So I'll give you a chance to think about that, and we'll talk about it in class. Finally here, let's define what it means for two functions to be equal. So we'll say two functions are equal if they're equal to each other as sets. So that's kind of weird, right? We don't really want to think about these necessarily. We want to be able to switch back and forth our mindset between thinking of them as sets and thinking of them in our standard way. So let's see if we can unpack this definition. So what does it mean that they're equal as sets? I know that f is just going to be a whole bunch of ordered pairs. So we'll just say that it's going to be some a comma b coming from some a cross b, where a is the domain of the function and b is the codomain of the function, such that that b is just equal to whatever f of a is. That's sort of our formal notation. And then g is going to equal the set, I'm just going to use different letters here, c and d, coming from potentially different sets, c and d, such that d is equal to f of c. Now, if these are equal as sets, so let's say I have some a b element, b and f, then that a b is also in g since they're equal. But the reason that's in g would mean that g of a equaled b. But right, for all a in a, I know there exists some b such that f of a equals b, because it's a function, which means that ab is an f. So for all a and a, I know that I have that a, b, and f, which tells me that g of a equals b. Right? And the same thing would be true going back. So that means that they must have the same domain, because they have the same starting elements. So they have the same domain. And I can make them have the same codomain as well. So I can say that f is equal to g if and only if f of x is equal to g of x for every element in that domain of f. Right, so that is what we want. They're equal if they have the same domain, they have the same or different codomains. They could actually be different for each other, right? I could say f goes from a to b, and g goes from a to d. These can actually be different even if the functions are equal. But we still get that those are equal as sets. Okay, I'm just going to change this guy to a D because I think it's going to make it more consistent with what we have up above. Great.